My name is Matt Demas. I run the technical strategy for our public sector business here at Liqid. I'm joined by Bryan Courtright. He's the Director of Solutions Engineering at ID Technologies. Good friend of mine. Do a lot of cool stuff together. So today we are going to talk about how we're going to make your infrastructure smarter, how we make that hardware smarter using Liqid dynamic composable infrastructure. So first off, quick agenda. Well, like I said, we're going to talk about what is composable infrastructure. That term has been around for a little while. A Gartner term, and some people consider one thing composable, some people consider another. At Liqid, we have I think a different definition than what you're probably used to hearing. Next, we're going to talk about how that works, how our composable infrastructure is built, the parts and pieces, how it's put together. And then we're going to get into some use cases for composable infrastructure. After that, we're going to get into Liqid's very unique composable NVMe fabrics that we have, and then how those are integrated into solutions that utilize Optane NVMe, solutions such as VSAN and others. All right, first slide. There is a strong demand in customers today, right? People are going to the cloud. They're going to the cloud for multiple reasons, right? Some of those reasons are, I want to have my resources available immediately. When I have a new requirement that pops up, I need to be able to go service that requirement, and the cloud gives me that flexibility. It gives me the ability to say, you know what, today I have, I want a system that has 2 CPUs, that has this much memory, has this much storage, has a GPU, go. And it just gives it to me. I'm able to run my workload, and if it's a short-term workload, I can get rid of it. If it's long-term, it's there, and I just get charged monthly for it. Customers are willing to pay a premium to have that flexibility and to have the capabilities on demand. There are other benefits to cloud, but that's one of the primary reasons for customers going to the cloud, especially for episodic type of workloads that come up and go away quickly. On-premise, when you're trying to do something like that, you have to have a lot of extra gear laying around for that potential, what if this happens? What if a customer needs this? What if a customer needs that? And it can be very costly and if you're not doing that, then you have to sit there and literally wait a 2-3 month cycle to go get through procurement, order gear, get it in place, get it set up and running. It's a long, tedious process, and when you're trying to manage your customers as IT departments, your customers' expectations, going through that process in today's time frame doesn't always make sense. This is the reason for composable infrastructure. We're going to give you that same flexibility that you get in the clouds, the AWS, the Azures, the Google Clouds, right? We're going to give you that same capability on-premise. So when a new customer requirement comes in and it says, hey, you know what? I want to have 2 GPUs and 3 terabytes of storage and 3 terabytes of RAM in a box. I go click, 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 and it's done, ready to go, delivered to a customer. I didn't have to go buy a new box, go get it delivered, or spend a bunch of extra money on boxes for the potential need of a customer down the road. All right, so how we do that. Liqid's composable infrastructure is very different than many others. Composable in the market today, most people think of composing storage into servers. It's a very common use case, NVMe over fabric, where I'm delivering disk that doesn't live in the server to my server. That is what most of the market considers composable infrastructure today. Liqid has taken that and expanded that well beyond just storage. So as you can see inside this graphic here, we have a server. That server to us is just consistent of CPU and memory. From there, I install an HBA into that server. Then that HBA connects me to our Liqid PCIe fabric. Being PCIe based is very important here because it gives us the absolute lowest latency. It also allows us to avoid any OS compatibility issues. Because we talk on PCIe, we go directly into the BIOS of the system, and we're able to make the devices appear as if they were locally installed into that box. So I'm now able to go get the same boxes all the time, small 1U, even half U boxes, and I can make them AI superpods if I want to, because I'm able to compose in these resources. From there, I take a chassis, and I can put whatever devices I want, whatever PCIe devices I want into those chassis. If I'm in an as-a-service data center, I may want to do networking, so I can go reconfigure networking on the fly. I may want to put GPUs, FPGAs inside these boxes. And these boxes are all basic sheet metal. There's not really a whole lot of brains behind them, but they are outfitted explicitly for these types of devices. So if I'm looking at GPUs or FPGAs, these boxes are cooled properly for those types of devices, powered properly for those devices. This allows us to avoid any sort of issues of saying, well, my server's not big enough to hold those, or I don't have the right riser slots for those. It doesn't matter. My server is just strictly compute and memory, and everything else goes into these generic chassis. I can do the same thing with storage. I can deliver NVMe over PCIe. You can also deliver it over a fabric if you want through our same Liqid software interface. So that's the actual how that we work. Let's move forward. So this is the logical side of how that works. So we talked about putting all of these devices into chassis, right? Those chassis then turn into pools of resources in our software. So having a JBOF full of flash, right, that becomes a storage pool. And those are resources now available to all the compute nodes inside of my fabric, right? Same thing with networking and GPUs. All those devices are now available to any compute inside that fabric. We even have the ability to take storage class memory and go mount that into the compute nodes to expand memory beyond the basic DRAM that's inside the boxes. So as you can see in this slide here, we are taking physical server resources, and we're mounting in those, mounting in disks, mounting in networking, mounting in GPUs as required. So when the customer asks for it, we deliver it on demand, send it back. And that is how composability works. Actually, Bryan, I'm going to have you take over for this slide, kind of talk about some of the use cases you've seen out in the field.
Yeah, absolutely. Thank you, Matt. So isolated resources is an issue that I've seen come up over and over again with a number of my customer sets. I've spent a lot of years working with the National Institutes for Health, for example. They do a tremendous amount of extraordinary research, but they have some recurring issues that come up over and over across all of the institutes that make up NIH. One of the big ones is isolated resources. So these guys have problems, especially the folks that have smaller environments. And I'm not talking tiny. We're talking groups that have 128 node clusters, 192 nodes. They're not small by any measure, but by true Department of Energy high-performance computing standards, they are not thousands of nodes. What they get involved with is, because they're smaller, because they have intermittent funding, it's very difficult for them to accommodate outlier requirements. It's difficult for them to be able to constantly be refreshed and maintain flexibility. So you look at these folks, they've struggled incorporating new storage technologies. DDN is a major player in that environment. DDN is an excellent storage provider, but they're expensive. There's a volume of capacity that you really need before DDN makes sense in a lot of these environments. So the ability to run software-defined storage in an environment like that could be very beneficial. You can run GPFS on the nodes in the cluster with Liqid connected directly to those external NVMe chassis. You can run platforms or software like Weka.io. They bring really unique capabilities into these environments that are not massive in scale. They also create an interesting ability around GPUs. A lot of these folks, they may have small GPU clusters. It's hard for them to keep them up to date with the most current GPUs in them. And it's hard for them to have the ability to tinker with their GPU to CPU ratios. They might be able to attain 2-to-1, even 4-to-1 GPU to CPU, but beyond that, it can be very difficult. With Liqid, it's very easy to do that. You start with a shelf that may have 4 GPUs in it, and you can easily expand that out and compose up to 16 to a single socket. That has real salience in the market today and in the industry today. You can do those kinds of things with a DGX box from NVIDIA, but again, the barrier to entry there is significant because those are expensive platforms. The other interesting thing that comes with the flexibility is the ability to bring in new GPUs and constantly refresh. Your nodes might be 2 or 3 years old, but the ability to bring in, say, a V100 today when you were running old K40s could make that cluster very salient and impactful again to the principal investigators in the environment running the science. So those types of things bring a great deal of flexibility to these customers. You know, we look at these folks and they've had some significant challenges as well. You know, these guys, they're principal investigators. It takes time for them to learn how to use new technology. It took a bunch of my old customers 3-6 months, sometimes even more, for all of their PIs to come up to speed on how best to leverage GPUs, how to optimize their code, etc. If you take this approach, you can bring a shelf in with 2 GPUs and let the PIs tinker and become familiar with the environment and the new capabilities before you make a significant investment. And then they can decide it's worthwhile. Our researchers understand how to use the tool. We can quantify the results. Let's buy the other 14 that go in this chassis and really make a significant investment. So Matt, I'm going to turn it back to you.
So thank you, Bryan. I want to kind of get into what Bryan was talking to a little bit about that NIH discussion, and we're going to kind of get into the use case of how Liqid would handle those problems. So in this slide is a generic 3-rack deployment, and again, this kind of, like I said, it's going back to that isolated resources discussion where I have some nodes that are compute nodes only, some nodes that are high memory appliances, and some nodes that are GPU nodes. This is very common in situations like HPC, AI as well, even traditional data centers when I'm trying to be prepared for different customer needs, right? I'm going to have different server types out there, right? These are all isolated. For example, especially in the HPC world, when I have a request that comes down that says, hey, you know what, I need 4 GPUs of this type to go run this job. And I'm going to look at my architecture and I go, well, I've got 20 GPUs that have 20 nodes that have 2 GPUs in them. I got 20 nodes that have 1 GPU in them. I got 10 nodes that have 4. And then I have another 10 nodes that have 16, right? Spent a lot of money on those boxes, got the 16 GPUs in them. I've got 100 extra nodes that are just compute-only nodes, so I can't use those. So I can only utilize the servers that have 4 or 16 GPUs in them, right? Well, the boxes that happen to have 4, they're kind of a perfect fit. But those ones with 16, I'm literally wasting all those GPU resources. Then I have GPUs in the other ones that are just not able to be utilized because they don't fit that requirement. Well, here in our reference architecture design, the top of this rack, you'll see high-dense compute nodes. We don't really care what manufacturer they are. They are, like in this case, it's a 2U4 node box that are, like I said, running ultra-high-dense GPU with memory built in. Then down below, we have chassis of GPUs. These chassis are able to be delivered to any node in this 3-rack pod. So if I want to deliver 20 GPUs to 5 servers, I can do that, right? If I want to deliver 4 GPUs to a vast majority of those nodes, I can do that, right? I'm far more flexible than I ever was before. I'm able to customize the hardware to meet the needs of the job that I'm running against that gear. I no longer have to go force fit my job into the gear that happens to be on hand. This goes well beyond GPUs. So FPGAs work the same way for us. In fact, we have the ability to reprogram those FPGAs on the fly. So if that's a use case that your customers are getting into, and I have a new job that comes in, it requires a new FPGA instruction set, I reload the FPGA, and I deliver it out to the compute nodes, and that job gets done optimally. The next piece is going to be your scratch disk. We can deliver Scratch disk is either whole drives to servers that mount into the BIOS as if they were locally installed. We can also do it in a over fabric method where we do large disk, small disk that can be sized appropriately to the exact requirements you have and mount that into the operating system. And the next piece is going to be that storage class memory. We have the ability to use storage class memory such as Intel Optane. A few other vendors have some storage class memory as well that can literally be secondary memory inside the box. So if I have high memory appliance needs, Oracle, high write databases, right? Anything that, or HPC type workloads, right, that need high memory appliances, I can actually create those on demand by composing that Optane or storage class memory into those servers to deliver it as wide as it needs to go or as deep as it needs to go. If I need a ton of memory into a system, I can do that. If I need a bunch of systems with a little bit more memory, I can do that as well. So it gives you complete flexibility in your infrastructure. And then on the left side, you see the single rack pod. This is just showing it can be done in a single rack where a share everything architecture. I can scale that out into a larger rack for share everything. That is how Liqid's PCIe composability operates in a data center environment. Now all these systems can be air cooled or water cooled. Everything in here is fully configurable. So if you don't need that many GPUs, you don't need that much NVMe storage, all of that's adjustable based on your requirements. Again, we utilize PCIe for the ultra low latencies. It really allows the devices to operate as if they were plugged right into the system. You don't have to worry about compatibility problems, something getting in the middle. Oh, that doesn't perform well enough because I'm composing it in. There's no composability tax because we're using PCIe. And then obviously the big benefit is extreme hardware utilization improvements. By not having those islands of resources, we're able to increase utilization significantly in these systems. So next we're going to talk about the Slurm piece. This is more around HPC in particular, but we've got some integrations with both Slurm and then Kubernetes as well from a container standpoint. So we talked about how the devices can all be shared, but I want to talk about practically. Like if I'm going to actually use AI or HPC or even containers, how am I going to go about doing that? And this is the way that process flow works. So if a user needs something, they're going to go to their tool of choice, right? This case being Slurm, could be Kubernetes, could be lots of things. It goes in, makes a request to your controller. That controller is then going to go to Liqid. It's going to say, hey, Liqid, my user asked for this. As you can see in this slide, user A asked for 3 servers that had 2 GPUs, say a terabyte of memory and 1 CPU, right? User B asked for something different. User C asked for something different, right? The controller asks Liqid, say, hey, can you give these to me? Liqid goes and creates those devices automatically. All this is done via API, so there's no user interaction here. Liqid then gives it back to the controller and says, hey, here's the composed servers that you're looking for, and then is able to hand those back to the user or start processing the jobs in a version of in the HPC AI realm. So it's able to do all of that automatically by using composability inside your data center. It makes it a very cloud-like experience without having to pay the monthly premiums of having a cloud service. Next, I'm going to talk about kind of shift gears a little bit. We talked about our PCIe composable data center fabric. Right now, we're going to actually take that same PCIe technology and bring that down into a device level. Liqid has a composable NVMe drives as well. Why this matters is when you're talking about delivering NVMe storage across the fabric, being able to deliver small blocks, small bits, and not just have to deal with large capacity drives is very beneficial. But it also allows us to drive the most amount of performance out of a drive by doing it this way. So our drives have multiple different form factors. You'll see on the left side, you see an add-in card. You see a U.2 card. Inside each of those, it actually consists of 4 M.2 sticks. So the M.2 stick is the one right there on the right side. Most people are familiar with those inside of a laptop or desktop today, maybe an internal boot device of a server. These are all enterprise-grade M.2 sticks. We put them inside of a drive. And what that allows us to do is actually completely utilize the bandwidth that drive plugs into. Today, standard NVMe actually only utilizes about a quarter of the bandwidth of the slot that it plugs into, so it's not able to deliver nearly the right amount of performance. By putting multiple of these M.2s on this drive, I'm able to deliver significantly higher capacities as well as write performance, in particular to the end user. One of the other neat things here is I can not only do NVMe, but I can also do storage class memory inside these drives. So with the addition of storage class memory, it allows me to do really neat things, especially in the realm of software-defined storage, where I'm able to create multiple disk groups because I have multiple Optane drives sitting on a card. I can put those in a box and deliver those out as both storage for say a VSAN or something like that, and I can also use them as memory when I'm composing them into my data center fabric. So next we're going to talk about those actual use cases. Bryan, I think we're going to come back to you to talk about how Liqid's VSAN solution is differentiating the market.
Yeah, thanks again, Matt. So this is an area where really ID got introduced to Liqid, and we started taking a look at it, and we recognized right away it brought some truly unique capabilities to software-defined storage and HCI infrastructure environments, hyperconverged infrastructure. So VSAN in particular really comes down to a couple of things. Flexibility and performance. That's what it brings to the table. For a long time, though, enterprise-level VSAN deployments were somewhat difficult. One of the biggest issues with those enterprise deployments was your VSAN cluster had captive storage. It was not extensible out to VMs in particular off cluster. So with VSAN 7, that's completely changed, and that brings a fundamental capability now to VSAN that really, in our view, makes it enterprise level. So now you look at VSAN with Liqid in particular, it facilitates the ability to actually build out all of those drive groups. In a configuration, you can have 4 drive groups with 8 capacity drives. It's very hard to do that physically, though, in most of the typical boxes that are out there. With Liqid and the ability to bring those drives externally, I can do that. And that has a material impact on the cost factor because VSAN is licensed per socket. If I'm only running 1 or 2 small drive groups in a node, I'm paying a lot per gigabyte for that VSAN license. If I'm running 4 large disk groups, that VSAN license gets spread across a lot more gigabytes and becomes a lot more valuable to me. So that's one component of this that's very interesting to us. The flexibility to also bring in different CPUs, AMD in particular, is also very interesting. It was more interesting before VMware's license model changed and we were able to put the large 64-core CPUs in a system and really get away with a very dense virtualization platform. But even now, with the new licensing model where it's limited to 32 cores, we can still get an awful lot of performance off of the AMDs and the refreshed Intels. From the performance perspective, Liqid's NVMe drives do bring absolutely unique capabilities, both around performance and cost. When we're running Optane NVMe, we're seeing 2.5x performance increases over SAS SSDs. That is significant. More importantly than the massive amount of IOPS even that these systems can deliver, it's the latency. That latency profile is really important. When I deploy a cluster like this, leveraging NVMe and Optane, I'm very confident that regardless of the workload I throw into the system, I'm able to support a latency profile that's acceptable. And that means a 4K write or 128K block size for my writes. It doesn't really matter. And this is important to the enterprise piece of vSAN deployments. I came out of Nutanix, and Nutanix had a really interesting metric. Most of their customers, actually the average for their customers was 3 disparate workloads or 3 different workloads per Nutanix cluster. But we had to be cautious. We had to make sure that the cluster could support the types of workloads that were within it. So when we use VSAN now, leveraging Liqid's proprietary drives especially, we see that we don't have to have care anymore about those workloads. We throw them all in there and we just let them run. That, from our perspective, is much more of an enterprise class system. So the next workload that I'm going to talk about is VDI. And this is also very interesting. So VDI, again, just like traditional vSAN and hyperconverged virtualization for server VMs, VDI is also all about flexibility and performance. VDI does need the high IOP, and it also needs the low latency. So again, those proprietary drives are very beneficial for that type of environment. If we look at the cluster that's represented here, excuse me, I'm showing 4 nodes. The ability to have 4 nodes support what it approaches realistically 1,000 users, 1,000 VDI users, and that's a concurrent number. That is not 50% concurrency or something like that. I can legitimately support high user count in a very small cluster. That's important to making VDI approachable from a cost perspective. Just like the Optane NVMe is important for making VDI able to provide a high level of user experience because of low latency. If we think about this cluster and envision what it may look like down the road, what happens if GPUs are needed in this cluster? There are options for how I deal with this. I could take these 4 1U nodes and I can plumb, so to speak, that infrastructure up front, bring in a pair of PCIe switches and a shelf. And I can be ready to now add GPUs on demand. I can start with a couple of GPUs and again, scale them massively as needed without having to spend a lot of money on that very expensive infrastructure piece up front. That's actually becoming more and more important in these VDI use cases because we're seeing the applications move to becoming much more visualization intensive. So our normal users, our knowledge workers, are now getting to the point where they could actually benefit from graphics acceleration, and our power users are coming to the point where they're really pushing the limits of these cards. We may not want to have, even though we have the ability to put 16 users to a single card or 32 users to an M60 GPU. We may want to have a lower ratio to have more memory per user available for these more demanding visualization tasks. Another piece that we bring to the table in those chassis, the ability to mix and kind of have a mishmash of GPUs in there. I can run quad rows, I can run T4s, I can run M60s. When the next version of the T4 comes out, I can put that in my shelf. I could put that in my environment as well without having to go to the expense of adding additional clusters or nodes to a cluster. So I take these expensive resources, I put them in a pool that's independent from my compute clusters. So now if we take that out beyond 4 nodes and we start thinking about what a really large deployment might look like, and we're doing a lot of very large deployments at ID. We're talking 5,000. We've done deployments north of 55,000 users. These are significant. We're creating pools where my CPU and memory exist in a number of clusters. And then I have a separate shared resource pool of GPU and possibly other resources that are independent from those clusters of nodes. So each of my little clusters is a fault domain, and I have a large pool of centralized, highly available, expensive GPU resource that I can now parse out however I need to. That becomes very interesting for these bigger deployments. So let me close out my piece. I want to take just a minute and talk about why ID became so interested in Liqid. It really goes back several years when I was at Dell. We talked about composability. Really, we were talking about disaggregation. And the discussion was how you radically reshape a data center. So let's think about a cloud service provider. Talk about Amazon. They've got rows and rows, tens of thousands of servers sitting in these racks and rows. They sit there without any sheet metal. The CSP, Amazon, AWS, Azure with Microsoft, they might not even replace a failed node, right? Node fails, they just ignore it and they move on. So think about what an enterprise data center would look like with disaggregated infrastructure put in place. I've got shelves of CPUs, shelves of memory, I/O, storage, GPU, FPGA, additional future devices. And I've got software that allows all of that disaggregated hardware to reorient on demand. That is what got ID very interested in Liqid. We're putting together an approach that takes that infrastructure and we map up with the movement away from VMs to containers. We look at the ability to build application lifecycle, right? That spans things like DevOps, through GitLab or other platforms. And it combines application optimization with tools like AppDynamics. And then it moves application orchestration into that model as well, where you can intelligently place applications where they best belong or where they most realistically belong. Steady state workload belongs on-prem from a cost perspective. It might go off-prem because of flexibility, right? When you bring Liqid and the rest of those pieces together, we really get to be able to build a unique infrastructure that is what we think a true next generation data center is going to look like. It's an infrastructure that your business requirements or your mission requirements can hit, and the infrastructure bends to those requirements, where previously that infrastructure would break. When it got hit by the business need, it would break. It couldn't react fast enough, and those workloads were migrated off to the cloud. So that's our big picture. That's what has us really excited in the long run. In the interim, the ability to take all of this infrastructure and support diverse workloads. Think about what we're showing here in my slides and then in Matt's previous slides. It's all the same hardware. My customers today are siloing AI, machine learning, high-performance computing away from enterprise data centers. With Liqid, the same infrastructure supports those very distinct workloads. That brings a massive amount of benefit right up front to the customer. Forget about our bigger vision and all the exciting things that does. Today, right now, being able to handle all of those requirements with the same infrastructure does a couple of key things. It reduces the cost, it reduces the risk, it speeds the time to value, and it enables innovation that's really difficult right now. So that single infrastructure pool dynamically shifts all of that now, and it makes our customers able to respond faster. So I've run on probably too long. Matt, I'm going to turn it back to you. Thank you very much for the time.
Hey, thank you, Bryan. Appreciate it. Awesome. Well, the last slide is just kind of recapping. We talked already dynamically reconfiguring systems, right? That is what we do. The running across that PCI fabric gives us complete flexibility to really prepare us for any situation that comes through. Independent scaling of resources, right? This is kind of what Bryan was talking about from the VDI perspective, right? When I need GPUs, I never know how many I need, right? So I'm sitting there trying to buy servers today for what I might need 3 years from now. So I gotta get all this space inside these chassis and go verify, because I don't know how many people are going to require GPUs in the future. All that goes away, right? I get to buy 2 U4 nodes for my VDI and put chassis in for GPUs. If I need more GPUs per user, I put another GPU chassis in, and I just connect it into the fabric. I'm fully flexible, prepared for whatever challenge gets thrown at me. And next is going to be that extended product lifecycle. So this comes into place again with what Bryan was mentioning. By disaggregating the GPUs, when the new GPUs come out, if I want to replace those early, I can replace those early. If I don't need to replace those, but my compute's going end of life, I can replace that. My server becomes a $10,000 item and not a $40,000 item anymore, because I've disaggregated all those pieces. It allows me to keep myself as up to date as I want to be, as well as making my procurement smaller. So they're easier chunks to handle. I don't have to wait till I have enough funding to go replace an entire rack of gear. I can say I'll do my compute this year. My networking doesn't need to be done for another 4 years, right? I'm not planning on upgrading from 10 gig to 25 or 40 or 50, whatever. I'm not planning on doing that for another 4 or 5 years. So those NICs are still good. I don't need to replace those, right? NVMe, I'm still happy with that right now. I replace the parts and pieces that I want to at that time. And that goes into the decoupling purchase procurement decisions as well. Well, thank you everybody for your time. I appreciate it. And if you have any questions, feel free to reach out to us. We're always here. And thank you, Bryan, for taking the time to come out and participate in this.
Yeah, thank you very much.